Hey, so welcome back to more LeetCode problems. So today what we're going to do is similar to yesterday. We're going to do more LeetCode problems from the famous Blind75 list. And so if you want to access this yourself, go to neetcode.io. I'll put the link in the description. And so this is a site from a popular YouTuber where he put this very, very famous list of these problems on his website, as well as links to those LeetCode problems. So you can just click on them and do it yourself. So basically yesterday I did the arrays and hashing category, but today we're just going to do the two-pointer category, which is a very popular problem pattern dealing with mostly strings and arrays, but really it could be anything where you kind of have 2 pointers on it. And I think just as I demonstrate and solve these problems with you, I think you start understanding the application of this problem type and just how to implement it yourself. So let's go ahead and do the first one. So this is an easy level problem called valid palindrome. And so what a palindrome is essentially, basically if you had an arbitrary example like this, if you read it from left to right, it would read the same thing. And so to prove that, I'm going to read this from right to left. So it goes A, and then it goes B, and then goes B, then A, then B, B, A. And so as you see from left to right, it reads like this, and from right to left, it reads the exact same thing. Another example of that would be if you just kind of put a mirror kind of in the middle of this string, you would see that reading it from inwards outwards spells the exact same thing. Another kind of quick catch here is that if you have an even number of letters, it would be something like this, or no, something like this. And so as you can see, when you have an even number, you don't have this kind of awkward middle letter here that has no equivalent match. And so every single one of these letters has kind of an equivalent match. All right, and so for this question, we want to see if the string is a palindrome. Now the catch here is you kind of want to do exactly what I just told you, but there are some changes here where we first want to convert all of these letters into lowercase. And so we can just basically remove these uppercases and just convert them to their lowercase equivalent. But then also, we only want to consider the alphanumeric characters, which essentially is just the letters and the numbers. And so we don't want anything like a colon or these spaces or exclamation points or say this comma. And so you can just trim those out. And after you do that, the way we actually prove that it's a palindrome, there's kind of two popular methods. One of them is to use 2 pointers like so. And basically you're just going to go from outwards inwards, and you're going to say, okay, does these two ones match? If so, let's move them in. And we kind of keep moving them in until they cross over. And so with each iteration, you're just proving that from outwards inwards, they're always matching. The other possible way of doing it is basically you just take this string and then you reverse it, and you just see if the original matches the reverse version, which is a quick hack. But because we're doing the 2-pointer method, we should probably do the true way of using 2 pointers, not the easy way. But yeah, let's go ahead and do this. So essentially, let's just iterate through for every letter in this string, and we only want to consider those that are alphanumeric. So if this letter is alphanumeric, which this is how you do in Python, and then basically we're just going to be creating a new string that's kind of been parsed and has been filtered and fixed so that we can see if it's a valid palindrome or not. And so we're just going to find that here. So with each iteration, we're just basically taking that letter and converting it into lowercase because we know it is alphanumeric. And so from here, we just want to prove whether or not it is in fact a palindrome. To do that, we just have to check, okay, check if it is a palindrome. And so basically as we move them from outwards inwards, we're just trying to find a reason that they are not the same. And so in that case, you return false. But if you're able to kind of reach the middle and they kind of cross over, then we just return true here. But inside of this for loop, or I guess this while loop, we're just looking for a reason for it to be false. And so to do that, all you have to have is a P1 and a P2, so 2 pointers. One starts at the beginning and one starts at the end of this string. And so we're just saying, okay, while the first pointer is less than the right pointer, so that means that they haven't kind of crossed over yet, or they haven't met in the middle. And so with each iteration, we're going to be basically decrementing the second pointer by 1, and we'll be incrementing the first pointer by 1. And so all that we have to see is, okay, if the letter at this pointer does not equal the letter at this pointer, then let's go ahead and just return false. But if you don't return false, let's just keep moving them inwards until we meet in the middle or find something that proves it's not a valid palindrome. Oops, trying to index out of range. So let's see here. P1, P2, oh, well, the length of S2. So the length of S2 will be different than S because we filtered out some of the characters in the original string. And success, so that's the first problem. Let's go ahead and do the next one. So this one's called threesome, and it's actually the kind of second question or the follow-up question of the most famous problem called twosome. And so for this problem, you're essentially given an array here, and you're just trying to find triplets that will add up to 0. And so the only catch here is that you got to make sure that there's no duplicates. And so essentially what that means is you can't have like, okay, there's the pair -1, -1, and 2. And then you can't also include, say, 2, -1, -1, right? Because they're just duplicates, or they're just kind of sorted around. And then the only other thing is you just got to make sure that you're using different numbers. And so you can't just keep using, say, just these 3 zeros when there's only 1 0. They all have to be like different indices, and that's described right here. All right, so to go ahead and implement this, essentially what we're going to do is kind of iterate what you do for a lot of kind of n-squared algorithms. And so we're just going to have one pointer that starts here, and then basically we'll iterate from that point on to the end, and then we'll repeat, but we'll increment this pointer forward. So now we'll go start here and basically go from that +1 onwards and so forth. And so you're basically just, it's like, I think it's how you typically traverse a two-dimensional array. It's like you have 2 for loops for I in the range of nums, and then it's kind of like for j in the range of I to the length of nums, like so. I'm sure that makes sense to you, right? And so you just want to make sure that you're just moving forward from this new starting point, and that would run in n-squared time. And so with that, that allows us to basically be looking at every single possible kind of combination of pairs, but we're dealing with triplets here. And so with that, the benefit is that we can basically see, okay, as I moves forward, we can kind of keep track of I and all of what it's visited in the past, and we'll basically consider that set of numbers as the third integer. And so what that will look like is we'll basically use something called like a hash set here, hash set. And so it'll allow us to look up a number in O of 1 time complexity of all of the numbers that we've traversed from this first pointer. And so with that, we can basically just consider those combinations. And so with these 2 pointers, whatever 2 numbers they're pointing at, we can basically take those 2 numbers, and let's say we're pointing at -1 and 0, and we'll basically add those together, which -1 plus 0 is then, well, -1. And essentially, we just need a third number that is equal to whatever number will make this 0. And so in that case, it will be 1 here. All right, if we give you like a positive example, it would be something like, okay, say we were given these two numbers, 2 plus 2, which equals 4, we would want then -4. So kind of just the inverse sign of the addition of those numbers. All right, and so essentially, we're just going to consider the ones that I has passed. And that just is a way so that we can kind of prevent some of the deduplication. There's another thing that we'll do, but I think I'll implement this and just quickly describe this extra thing that we'll have to do later on. And so what we'll have is seen, and that will be the set of numbers that we've basically kind of traversed past. And so that will occur here. So after this entire iteration, we'll want to add to our scene I, because this is the number that our front point, or our back pointer, I guess, really has passed. And so what we want is to consider, okay, what's our third num? So ij, and we'll set it as k as that third number that we need. And so it's going to be equal to the sum of these two numbers. And so then the number that we actually want is going to be the inverse sign of it. And so essentially, that means that, okay, then the number we want, so I guess we'll set as k2, will basically be the absolute of k if k is less than 0. So if it's a negative number, we want a positive. Otherwise, we'll want the positive number or the negative number. So that will be negative k. All right, and so essentially, if then that number that we want is in our scene, then let's go ahead and add that to our array here. So, which will be kind of returning at the end here. So then our response will basically be appending this set of numbers. So number at I, number at j, and then this new number, which is k2. But the only catch here is that we'll still have occasions where we have duplicates. And so to prevent that, all that we have to do is basically keep track of the hash of this. And so what that will be is, say if we have the numbers -1, -1, and then 2. And so in that case, basically we're just going to sort this, which is kind of already in sorted order, by like increasing order. And then we're just going to convert it to like a string. And so that will allow us so that when we're looking for duplicates, we can just quickly look up in our historical triplets here if there's a one with this exact same hash. All right, and so basically we'll have another set called used. And so in that case, we'll say, okay, if k2 is in scene and then this triplet, or really the hash of it, is not in used, and our hash is not in used. And so basically our hash will be this triplet there, but we'll have it sorted, and then we'll also convert it into a string here. And so this is our hash. All right, and so then the only other thing that we'll want to do is basically just add this hash to our used.add our hash. Oh, looks like we have a problem here. Let's see. So, so it looks like we do have duplicates, but I don't see 2, -4, 2. So we want to consider from I plus 1, and that just makes sure that we don't accidentally reuse numbers that are only one occurrence of it, because this example we only have 1, 2, but it was using 2 2s. So let's fix that. And then, did I do it? I plus 1, yeah. For I in that range, for j. Oh, C not at I, no. We want the number at I. There we go. And success, so that's that solution. And then finally, let's go ahead and just do a container with the most water. And so with this, it's essentially like the first problem, where we're going to be kind of going from outwards, inwards with these 2 pointers. And so what this problem is asking is, okay, what is really the container in these sets of containers that will kind of can carry the most water? And so what that means is these are basically like, I guess, walls. And this is water here. The blue is marked as water. And so if you had these 2 walls used, you would be able to have this much water filled, which is a total like volume of 49. And so that is much more than if you use, say, these 2 walls. So if you use this wall and this wall, the water would be like this, because you have to take the minimum height here, because you can't really have slanted water. And so the water would only fill up like this volume, which is much less. It would basically be a height of 1 and a length of like 1, 2, 3. So it would be basically 3 versus this is a total area, I guess, of 49. And so we could look at another possible case. Now, although this one is higher than this wall, it only gives you like 1 extra height boost for being at this wall, but this one has like a distance of 2. And so choosing these 2 walls provides a greater area than necessarily these 2 walls. All right, and so essentially to do this, all that we want to do is have 2 pointers. One starts on the left-hand side and one starts on the right-hand side. And we'll basically calculate the volume, or I guess the area. And then after we calculate that area, we can see, okay, is this the maximum area we've seen so far? If so, let's keep it. Then we move one of these pointers, and we're just moving the pointer with the lower height inwards. It's kind of a greedy approach where it's like, okay, whichever one of these, so we start here and we start here, we calculate their area, which would basically be this space here. And then we're just saying, okay, after that, let's just move one of these 2 pointers, whichever one's shorter, and basically it's this one. So let's move this one inwards, and then let's calculate, well, this new area. And then after that, we're just going to move it inwards, whichever one's shorter, which is this one, so this, and we have this pointer still here, and then we calculate its new area. We see, okay, is this new area the new maximum? And we keep doing that until they reach the middle. All right, so let's go ahead and implement this. So basically, we're expecting to return some max area, and that's going to be initially equal to 0. And then we're going to be using 2 pointers here, pointer 1 and pointer 2. Pointer 1 initially starts at 0. The second pointer starts at the end of this array, so the length of the array -1. And then also, well, this max area starts at 0 still. And so, like, again, we have this pattern of while the first pointer is less than the second pointer, and so with each iteration, we're expecting to move one of them inwards. But we also want to be kind of calculating this max area. So let's calculate the new max area. And so all that will be is basically the max area is, or I guess let's just calculate the current area, which will just be the array at, or the height at P1, and the height at P2. And so we're just going to take whatever is the minimum, right? Because the water can't be slanted, it can just be at the total height. So if we're considering this and this, the water can only be this tall, so that as tall as the shorter one. So that's why we take the minimum, and then we're just multiplying it by the distance between them, which is just the P2 minus P1. So we just take the X location here and subtract it by the X location of the other pointer. So now we have the current area. Then we want to find the new maximum, which is just the maximum of the current max area and then the current area size. All right, and so after we calculate the new max area, we just have to move the smaller height inwards, or whatever pointer is pointing to the wall with the smaller height. And so if the wall at P1 is less than the wall at P2, then let's move P1 upwards towards the middle. Otherwise, we just want to move we want to move P2 inwards. Since it starts on the right, we want to move it downwards, or I guess decrement it, so that they both kind of reach the middle of this array. Looks good. And success. So yeah, that's another O of n time complexity. I think I didn't describe the space complexity or the time complexity for these. So for this one, it just runs in O of n time and O of 1 space, because we're not using any extra data structures here, just variables. For valid palindrome, let's take a look at that one. I believe we just look at my previous submission here for it. So it is also O of n because you're just traversing each element once, so as we move them inwards. And then it's also O of 1 space complexity because, well, we're not using any extra data structures. The only catch here is with the problem called threesum, where the time complexity is going to be O of n. We're doing some sorting here, but it's just like O of 3, so that's static in length or constant in length, so that sorting doesn't really matter. So really this is the bottleneck for space complexity, or for time complexity, is this n squared algorithm. And then for space complexity, well, we're using these sets, which can be at most O of n, and so that's O n squared time and O of n space complexity. But yeah, this is the Blind75 two-pointer category. I hope that helped a little bit, and watch more. I'll be doing sliding windows next, and good luck with the rest of your algorithms. Thanks for watching.